Hello, everyone. So welcome to today's seminar. It's a pleasure to have Dr. Semi Yu to give us a talk today. So Dr. Yu is a senior lecturer with the University of Glasgow at the School of Engineering. He is an expert in the field of environmental and energy systems, focusing on the water treatment and waste management. Before he joined the University of Glasgow, Dr. Yu has worked as a postdoc fellow at MIT, NUS, and NUS. He received his PhD degree from the Nanyang Technological University in 2014. And Dr. Yu has received several international awards from the American Institute of Chemical Engineers and the International Bioprocess Association. Dr. Yu is leading several large research projects related to the life cycle assessment and the optimization of waste management and water treatment. So let's welcome Dr. Yu. Dr. Yu, we look forward to your talk.
Thank you, Sri, for the kind introduction. And indeed, it's my great pleasure today to share a bit of research with you all today. So what I'm going to talk about today is on the environmental footprints of bioenergy production and waste management and the relevant application of machine learning methods. So basically, the whole talk will be split into two parts. The first part will be kind of like a few case studies on understanding the environmental footprints of waste management, different waste management schemes in the UK, more specifically in Glasgow, for example. And then the next part will be about how we're trying to apply machine learning to improve our data quality for relevant analysis. Okay, so why we trying to focus on the waste management? First of all, it's a significant challenge worldwide. So by 2025, it's estimated that about 2.2 billion tons of municipal solid waste will be generated. And in Scotland, the government also sets up very ambitious goals to reduce the environmental footprint related to waste management. For example, it aims that no more than 5% of all waste will be landfilled by 2025, and 70% of all waste will be recycled, composted, or prepared for reuse by 2025. And the UK, as a whole nation, aims to reduce greenhouse gas emissions to reach net zero by 2050. So waste management is a major issue in modern cities and across the world. But at the same time, it bears opportunities for carbon abatement. And in the following a few slides, I'm going to show that how it's possible and how we're trying to understand its carbon abatement potential. The first kind of case study we did is about to understand some kind of different waste management schemes to be deployed in Glasgow. So in Glasgow, we have about 30 million bins of connections every year and about 350 kilograms of household waste generated per annum per capita. And our existing practices in Glasgow is that we have a very big recycling and renewable energy center. It's a centralized large system based on two technologies. One is anaerobic digestion, another is gasification. So it's helped to treat about 222,000 tons of waste every year. So that is our existing technology. And these systems helping to handle including, for example, food waste, garden waste, and other organic waste, as well as paper, cardboards, etc. So what are the environmental footprint of waste treatments that are at a smaller scales and at a or more decentralized mode? So this is the first question we are going to answer. So again, we are considered still two technologies that is relevant. One is anaerobic digestion, which is devoted to treating organic waste. Another is gasification technology. And for the analysis, we consider the anaerobic digestion technology as a two-stage mesophenic and anaerobic digestion, and in a continuously stirred tank reactor. So this is also one of the most commonly deployed configuration for anaerobic digestion in the UK. And we consider a digested production rate of 500 kilogram per ton of waste treated, and the biogas yield is 350 cubic meter per ton of volatile solid, and the methane content is 60%. Well, for gasification technology, we'll consider a common technology deployed in the UK, which is a moving grade reactor, which is suitable for feedstocks with high moisture contents, such as organic fraction of municipal solid waste, and is also suitable for handling non-uniform morphology of municipal solid waste. We'll consider air to be the gasifying agent. Solid residue is 50% for soil management. So this is how we consider how we're going to use the solid residue generated by the technology. By the way, if for those who are not probably familiar with these two technologies, anaerobic digestion is the biochemical process that make use of microorganisms to decompose an organic waste to generate a gas called biogas, which is mainly consists of methane and carbon dioxide. Well, gasification is a thermochemical technology that's going to be used to treat carbonaceous materials to generate a gas called a synthesis gas, which consists of components such as hydrogen, carbon monoxide, and also a small amount of methane, mainly. So we can see the three scenarios, and the name it as 6A and G, which corresponds to 6 townships using both AD and gasification. 6G, which is corresponding to, okay, we divided Glasgow into 6 townships, and with each township, we having a gasification system deployed, and also 3A and G system, which corresponds to 3 townships using both anaerobic digestion and gasification in each township. So this table shows input parameters for the anaerobic digestion and the gasification technologies were considered. Here we consider, okay, the biogas generated by the anaerobic digestion system will be fitted into a combined heat power generation for generating heat and electricity, which will be then fitted into satisfy the energy demand of local communities. And similarly for gasification, its syngas will be fitted into combined heat power generation system to generate electricity and heat. So now I'm going to explain a little bit more about the life cycle assessment we use to carry out the analysis. So first of all, here I just cover some major points, and more detailed information could be found in the original publication. And the functional unit we consider is about treatment of 1 ton of municipal solid waste. And this division of different types of waste in that 1 ton is based on their waste statistics for Glasgow. And in the system boundary, we consider electricity and heat generated to substitute electricity and heat generated from natural gas. And because we consider different configurations, 3A and G, 6 and A and G, so they correspond to different amount of waste generation, and that's different capacities for the systems required. So for larger plants, larger systems, like we increased the process efficiency from 34 to 40% to account for the influences of system capacity on the process efficiency. For the anaerobic digestion, we consider 3% leakage loss, and the syngas generation is 2,600 cubic meter per feedstock treated. In this case study, we are more focused on comparing the three different scenarios we defined. So we consider the same municipal solid waste connection process, which is about transporting the waste from the connection point to the waste treatment facility. And correspondingly, the transport distance for the 6A and G and 6G scenario are 16 kilometers. Well, for 3A and G, it's 32 kilometers. And for the emissions related to transport, we model using the inbuilt Gabi processes. What we did is that we tried to estimate how much diesel is required for this process. And then we used inbuilt Gabi processes to estimate the emissions related to the production and the combustion of diesel upon its application. And for this estimation, we consider a Euro 5 truck for the transportation of the waste and a utilization factor of 0.5 to account for empty return trip. Well, for the transportation of glass, metals, and electronic waste, we consider a Euro 3 truck. So the figure here shows the system boundary we defined for this case, and the values in brackets indicate gasification pathway. In the life cycle assessment, we consider three impact categories, which are global warming potential, acidification potential, and eutrophication potential. So now, first of all, let's look at the energy generation of these three different types of development. So for the 6A and G development, the energy generated could be used to fit or satisfy their electricity demand of about 10,000 of households, which is about 20% of local households in the communities that's served by the 6A and G scenario. Well, the corresponding numbers for 6G and 3A and G are about 9,900 and 23,000 households, which are correspondingly about 90% and 23% respectively. So this is for the electricity generation. For the heat generation, we considered for the considered three scenarios, they could satisfy up to 5% of energy demand of the households. Now let's look at the life cycle assessment results. And we found for the three scenarios considered, they could generally avoid about 350 kilogram carbon dioxide for each ton of waste treated. And also the electricity displacement, its impact on the three impact categories analyzed is generally greater than the heat displacement. Transportation has a major impact on global warming potential, but its impact on acidification and eutrophication potential are significantly higher. 6G scenario considered to be the preferred alternative for reducing the global warming potential, and these three scenarios achieve similar eutrophication potential and acidification potential. And then following that, we did a very simple sensitivity analysis. We try to evaluate a few major parameters. The first one is the heat utilization rate. So in the baseline scenario, consider, okay, all the heat generated could be fitted into or utilized by the communities. But in reality, the energy generated might not be, say, be able to consumed by the nearby communities. So we consider alternative cases that have a heat utilization rate of 50% and 0% respectively, and then explore how it's going to impact their global warming potential. We also change the biogas leakage to 10%, consider a more worse scenario for the biogas leakage anaerobic digestion system. We found that for the biogas leakage of 10% is increased global warming potential from about 562 kilogram to 614 kilogram carbon dioxide equivalent, while the AP and AP are not affected by this leakage. Well, for the heat utilization rate, when it's reduced to, say, 0%, then it could reduce the carbon saving of this kind of development by 1/3. So that is the kind of first case for the waste management in Glasgow. And then the second case is more specifically on food waste management in Glasgow. And in this second case study, we explore the possibility of deploying the anaerobic digestion systems in even smaller communities, and thus smaller systems, and see how that's feasible from an environmental perspective. So first of all, the food waste has been always considered high priority waste streams. It's with significant social, economic, and environmental consequences. Prevention is the key factors, but unfortunately, not all food waste are avoidable. So here we're going to explore when we divided Glasgow, the city, into 23 zones or townships, kind of based on their 23 electoral districts, and see what's the environmental footprint of such small-scale system development in the small areas in Glasgow. And we'll consider the food waste to be collected every fortnight by refuse collection trucks, and the biogas being combusted in combined heat power generation to generate heat and electricity. So this is similar to what we explored before for the first case. And electricity is being fed into the grid, and heat being used by local communities, while digested is being supplied to local farms as a kind of to displace fertilizer. So this table shows the input parameters for the anaerobic digestion system and the combined heat and power generation. Here we consider a biogas yield to be 105 cubic meters. So this is considered to be a conservative number because in the literature there have been values up to 156 cubic meter per ton of wastewater, wet waste being treated. So we use our conservative data so that our analysis will be more kind of realistic. And for the food waste production, it's about 70.7% of about 480 kilogram of municipal solid waste generated per year in Glasgow. And then we multiply that data with the population of each individual ward to estimate their food waste generation in the wards, and then the food waste amount generated in each ward being used to define the scale of the systems for the energy production estimation. Here, one different thing from the first case is that we're trying to use a more sophisticated model to analyze the waste connection or transportation process. We reviewed those existing models. The first one is the organic waste research model, which is developed by Swedish researchers. The second model is the waste recycling and cost model, requiring data on average road speed, set-out rate of bins and truck capacity. And this model is developed by Australian researchers. The third one is a relatively recent one, is the MSW Connect model that could be used to predict the energy, the time requirement for the transportation connection of the waste. So we consider this model in our study because it's evidence to be able to provide more accurate data about the energy and time requirement analyzed. So now I will talk a bit more about this connection transportation model. So in this model is basically divide the waste connection transportation into three stages. So the first stage is the urban haul and return. Distance between center of any connection area and the point where waste is uploaded. And by analyzing these three different stages and getting the time and energy requirement, and then we sum the time and energy requirement for each stage to estimate the overall time required for connection and transport waste, as well as the diesel required for connection and transporting the waste. So by using this model, we estimate for our case defined, the diesel requirement is 2.95 liter per ton of waste connected, and the truck time required is about 0.83 hour per ton of waste treated. This needs us to decide the number of trucks required is 25. So now I will talk a little bit more about the life cycle assessment carried out. So it's basically about evaluating a community-based distributed food waste treatment scheme in Glasgow regarding three impact categories, which are global warming potential, terrestrial acidification potential, and the particulate matter formation. And the functional unit is treatment of 1 ton of food waste. And the figure here shows the system boundary. It includes the food waste connection transportation, anaerobic digestion to generate biogas, and also the biogas utilization, combustion in the combined heat power generation to generate heat and electricity, and the heat and electricity being used to displace the heat and electricity generated from natural gas. Well, for the digestate from the anaerobic digestion, we consider it being transported to a nearby farm and used as to displace a digestate. The biogas leakage, similar to the previous case from the baseline scenario, is 3%. And the emissions due to waste connection are estimated based using two inbuilt garbage processes. The first one is the diesel mixed at a refinery, which we use to estimate the emissions related to the production of diesel. Excuse me. The second one is a dump truck payload inbuilt process that help us to estimate the emissions related to the combustion of diesel in the truck. Well, for the avoided emissions from electricity and heat displacement, we consider electricity from natural gas, this inbuilt process in garbage, and also the thermal energy from natural gas. Here we particularly analyze their avoided emission or their emissions related to the digestate application. So we consider the digestate being transported and spreading in their a typical farm in Glasgow, and we consider the distance involved is 20 kilometer, and for typical truck transporting digestate, we consider is 15-ton tractor that used to spread their digestate on farm, and for the on-farm transportation, the average distance is 2 kilometer. So we use that transportation connection model then to estimate the connection transportation for of the waste and the associated emissions. So to further add on that, we add these emissions from transportation spreading into that to account for their emissions related to transportation spreading of the digestate in the system. For the avoided emissions by digestate as a fertilizer, there are three aspects or factors we've considered. The first factor is that in order to estimate the avoided emissions by digestate, we first of all estimate the carbon, nitrogen, phosphorus potential in digestate using or based on the British food waste composition. And then the carbon storage of in the digestate is being considered by applying an emission factor of 0.09. And then this will be multiply with the amount of the digestate to give us the number about the carbon state storage related carbon abatement in digestate. Well, for the nitrous oxide emissions, we calculated based on the digestate nitrogen content with a factor for nitrous oxide to nitrogen of 0.015. And then these emissions being further converted to carbon dioxide equivalent emissions based on the characterization factors. The last factor we consider is that the digestate will be used to displace those chemical fertilizers. So we calculate how much chemical fertilizers will be replaced, and then that amount being used to estimate the saved carbon or greenhouse gas emissions about the application of digestate. For the results, again, first of all, let's look at energy generation. So for this small, I think even smaller scale of anaerobic digestion systems for communities, for each community, they could use to cover about, for electricity, 3,200 local households. For the heat, it's about 1,080 local households. So this is based on their biogas yield of 105 cubic meter per ton of waste treated. Of course, when the biogas yield could be even higher, as reported by literature, then more household will be able to be covered by this kind of development. For the life cycle assessment result, we find for the global warming potential, excluding biogenic carbon, this kind of small scale development could save about 92 kilogram of carbon dioxide equivalent. Similar to the first case study, we find that the displacing electricity, its impact on the global potential is higher than displacing heat, and which is further higher than displacing digestate. Well, for those major greenhouse gas emitters in the case study, the biogas leakage, its impact is greater than the waste connection transportation, which is further greater than the combined heat power generation combustion. If we consider biogenic carbon dioxide, then it could be substantially change the global potential. For example, the combined heat power generation emissions will increase from 31 to about 224 kilogram carbon dioxide, and the digestate related emissions will increase from about 56 kilogram carbon dioxide equivalent to 225 kilogram carbon dioxide equivalent. For the acidification and the particulate matter formation, they are mainly dominated by the combined heat power generation. And combined heat power generation contributes significantly to all three impact categories in terms of carbon saving. So it suggests that post-combustion carbon capture and storage is important for further reducing the global warming potential of this kind of development. So this is the first two case studies. So the three case studies, we further expand the consideration of food waste to and incorporate the management of cow slurry, because cow slurry is, I think, receiving attention by industry. So, for example, I think 2 years ago, the news says that the cow slurry is kind of harmful to the cows in the farms itself, and at the same time, companies, industries trying to figure out how to better utilize the cow slurries or manures generated in the farms. The companies try to convert it into used for transportation. And recently, they considered about generating biomethane to displace the natural gas utilization in the grid. So what we're going to consider is that not only about handling cow slurry, we're going to handle both food waste and cow slurry, and we're going to convert these two organic waste into biomethane to displace the natural gas using the Dutch anaerobic co-digestion technology, and the digester is considered to be a biofertilizer still. And the objective of this case study is to understand, okay, what is the environmental footprint of that kind of development in Glasgow? In order to generate the biomethane, we need to upgrade biogas. So we need to compare different technologies available. So we consider the four technologies. The first is the pressurized water scrubbing, which is based on the solubility difference of different gases and upgraded. The second one is chemical scrubbing, which is about using solvents for separating the gases. The third one is membrane separation, and the first one is the pressure swing adsorption. And this figure shows that illustrates the overall idea of this development. So we have the food waste from the local households, from cow slurry from the nearby farms, and we generate biogas, which is got upgraded to generate biomethane, and digested being supplied back to the farms as a fertilizer. For the anaerobic digestion technology, we consider is to be a wet mesophenic technology, and the mixed ratio between food waste and cow slurry is 1 to 1.8, and the methane content in the biogas is 60%, as we considered before. And the food waste considered is coming from the 23 wards, while the cow slurry is from the farms of South Lanarkshire, which is a major council in the south of Glasgow. Again, we still used MSW Connect model to estimate the time and energy required for this kind of development. For the more details of the life cycle assessment, first of all, the objective or goal of this study is to compare the global potential of biomethane production based on food waste and cow slurry co-digestion. We specifically compare different biogas upgrading technologies. The functional unit is the treatment of 1 ton of organic waste, consisting of 360 kilogram food waste and 640 kilogram cow slurry. The scope of the study of the system boundary we consider includes the processes from the point of waste connection to the injection of biomethane into the grid. And to here, I'm going to explain a bit more major point about life cycle assessment, particularly the life cycle inventory analysis. So we consider the avoided emissions of this new development as compared to existing waste treatment, which includes about avoiding this kind of waste to be treated by nanofuel and incineration, as well as avoid the emission related to slurry storage in the farms. For the connection transportation, we used a similar inbuilt process models in Gabi to estimate the production and combustion of diesel in the processes. And for the AD plant operation, we consider it requires 0.13 kilowatt-hour of per ton of waste treated, and this being further combined with inbuilt process Euro 28 electricity grid mix to estimate the emissions related to AD plant operation. For the digester application, we consider avoided emission to be 26.66 kilogram carbon dioxide per ton of feedstock treated. And for the upgrading plant operation, we consider the energy consumption required by different technologies, as shown in this table, and then combine these electricity consumption with the inbuilt process in Gabi, which is U28 electricity grid mix, to estimate the emissions related to upgrading plant operation. So for the results, let's first of all look at the efficiency and the energy production. So we found that chemical scrubbing is the most energy, generate most energy, and thus could be used to power most households in this kind of development. The membrane separation technology is of the highest efficiency, which is 83%. It could be used to power about 2,252 households, while the PSA technology is of the lowest efficiency, which is about 60%. For the life cycle assessment result, we found the co-digestion development could reduce global potential up to 264 kilogram carbon dioxide equivalent plutonium waste treated. And for the waste connection transportation, it's accounted for about 7 kilogram carbon dioxide equivalent plutonium waste treated. And for the plant operation, it's contributed to about 6 to 15 kilogram carbon dioxide equivalent plutonium waste treated. So this is about upgrade plant operation. So this number varies, depends on the technologies utilized. Well, the biogas leakage is still a very significant contribution to the global potential, which accounts for 22 kilogram carbon dioxide equivalent plutonium waste treated. Well, the digester application could help to save about 27 kilogram carbon dioxide equivalent plutonium waste treated. The largest carbon saving is coming from the natural gas displacement, which is about the major, I think, benefits of this kind of biomethane development. Compared to the different biogas upgrading technologies, we found PSA is less favorable due to its high off-gas emissions and thus relatively higher carbon footprint. So the previous ones is about waste management case studies, kind of we analyzed for Glasgow. And now I'm going to talk about a life cycle assessment we carried out to understand the biodiesel development in the UK. So it's not restricted to Glasgow, it's about UK's biodiesel development. So for biodiesel development, we consider the feedstock is rapeseed oil because about 50% of biodiesel in the UK is generated from rapeseed oil. And for the biodiesel from rapeseed oil, for the life cycle assessment, we consider 4 major stages or processes related to development, which includes rapeseed agriculture, and seed preparation, oil extraction, and biodiesel production. For the biodiesel production, we consider typical transesterification technology, which is about the use of alcohol and a base catalyst to produce biodiesel and the byproduct, which is glycerol. And also for the whole development, ranging from agriculture to biodiesel production, we also receive some other byproducts, which are rape straw from the agricultural process, rape meal from oil extraction process. One important things we explored in this study is that we consider different scales of development and how the scale differences going to affect the carbon footprint differences. For life cycle assessment, the function unit is about production of 1 ton of biodiesel, and we'll consider 2 scales, one large scale, another is small scale, based on the technical feasibility of biodiesel development in the UK. So for the large scale development, as shown in this figure, it's kind of like a centralized concept. And we'll consider a seed crushing plants in Hull, which is here, because there's already a seed crushing plant in Hull. supporting this kind of development. And these seed crushing plants receive rape straw from several locations in UK, and then their biodiesel production will happen in a nearby place called Immingham. So the biodiesel production is going to happen here by receiving the rapeseed oil from the hull. For small-scale development, we consider a scale to be smaller than 50,000 ton biodiesel per annum, and the rapeseed feedstock grown by nearby farms. And this plant is located to Suffolk, which is considered to be with a leading rapeseed farming systems there. For the system boundary, we consider, as just mentioned, the 4 major stages involved for biodiesel development. And I will then explain one by one. The first one is rapeseed agriculture. We consider cultivate rapeseed by following the guidelines by New Holland Agriculture, which is adapted to the UK context based on the Farm Management Handbook. For the large-scale development, rapeseed agricultural cultivation is that, first of all, the cultivation is initiated by subsoiling, which happens every 4 years, and then the soil being planted and minimum night tillage happened. Following that, seed will be sowed and rolled onto grounds, and then fertilized, used twice the pesticides 6 times for each cycle farming. And then the rapeseed will be harvested using a combined harvester. For the small-scale development, rapeseed agriculture is kind of similar, but for example, the pre-treating will be the same as the large scale, but the subsoiling will be excluded as suggested by the Farm Management Handbook. And the seed drilling rate will be lowered because for the Suffolk, this place was considered it has a relatively higher fertile soil. For the seed drying and cooling, we consider a green dryer, which is run via power takeoff shaft connected tractor, and it's cooled with 2 fans for 12 hours per day. For the oil extraction and refining, for the large system, we consider a seed crushing plant, which could handle 750 tons of rapeseed every day. This will generate 420 tons of rape meal and 323 tons of rapeseed oil. The rape meal is being further utilized in the current solvent extraction, which is used to further reduce the oil content in the rape meal. And then the remaining rape meal being treated in the steam-operated dissolventizer, which is used to remove the hexane. The extracted oil is being distilled to remove impurities, including hexane and water. So the small-scale development, we consider a cold press oil extraction technology, which includes cleaning, cold processing, filtering, and storage for sub-processes. And we'll consider the cleaning to be done by using a grain cleaner, and then our screw press will use to do the cold processing of the rapeseed, which is fed by a hopping process. And in the end, the oil being filtered using a plate and a frame filter. For the biodiesel production, for large-scale development, we consider 5 stages, which are storage and capacity stage. The second stage is a transesterification stage. The third stage is the cholesterol recovery stage. The fourth stage is the methanol recovery stage. The last one is the biodiesel purification stage. For the small scale development, similar 5 stages involved. But its use a 100-liter semi-continuous batch biodiesel reactor. For the transportation, we consider different distances for the large scale and small scale development. The large scale, the transport distance is 505 kilometer, or small scale is about 102 kilometer. The fertilizer utilized in the cultivation of rapeseed include urea, triple superphosphate, muriate of potash, and ammonium sulfate. So this is the common fertilizer being utilized in agricultural activities in the UK. And after estimating the amount of the fertilizer utilized, we then multiply with their corresponding global warming potential conversion factors to estimate the emissions related to the use of these fertilizers. In the life cycle assessment, we consider 2 impact categories. One is the global warming potential, another is the cumulative energy demand. In the end, we carry out a sensitivity analysis to understand the influences of changes in the process designs on their environmental footprint of the development. So now let's look at the results of the life cycle assessment. We find, first of all, rapeseed agriculture and biodiesel production are the 2 highest consumers of energy. For the large scale system, it consumes 72% of energy, while for the small scale, it consumes 92% of energy. And also the rapeseed agriculture is the highest global warming potential contributor. For large scale development, it accounts for 69% of global warming potential, while for small scale, it accounts for 81% of global warming potential. The contributions from seed drying, cooling, oil extraction, oil refining stages are generally minor as compared to agriculture and biodiesel production. Okay, so let's look at the emission breakdowns. The first one, we're going to explore the agriculture stage because it's the major contribution to the energy and the global potential. For the agriculture activities, we find the fertilizer is the major contribution to this stage, followed by their diesel usage. So this is applies for both agriculture, large scale and small scale development. And for the fertilizer utilized, the urine and ammonia sulfate of the highest cumulative energy demand and global warming potential footprint. And we found the small scale needs more, has more carbon footprints in relation to the use of fertilizer. This is because the small scale development needs more land than large scale development, and thus more fertilizer. And for the subsoiling process, the larger scale development will require, will have higher diesel consumption related global warming potential as compared to the small scale development. And for the methanol related global warming potential, large scale, the small scale is greater than the large scale. This is because the methanol process generated in a small scale development it's not considered to be recycled, while for the large scale development it's considered to be recycled because of the technical feasibility considered. Okay, so now let's explore a bit about sensitivity analysis results. We basically try to vary different operation conditions based on their practicality of biodiesel development in the UK. So the first thing is that we try to consider high rapeseed yield in the UK, and we increased the large scale to 3.4 ton per hectare and 3.6 hectare per hectare for small scale development. This will reduce the global potential by 14.1%. The second factor we consider is about using the biodiesel, so B20 fuel for their processes. This will reduce global potential by 1.1% for large scale development and 1.2% for the small scale development. And for the oil extraction technology utilized by their small scale development, as we previously considered, its extraction capability is relatively small as compared to large scale development. And thus we try to explore what if the extraction capability is being increased technically from 30% to 36%. In that case, the global potential will be reduced by 14.3%. And for the transport distance, we consider the variation of transportation distance by considering the plants to be deployed in the central belt of Scotland, which is less populous. So in that case, the distance will be significantly increased by 74%. So this will increase the global wind potential of large-scale development by 1.7%. And for small-scale development in Scotland, we consider if we double the distance, then the global potential related to the transportation will be increased by 1.9%. Alternative ways of improving the carbon footprint of their development is by utilizing the biomass generated during process, that is rape meal and rape straw. We consider to combust those biomass in a biomass-fired boiler and then supply that heat to the process. That could help to reduce the global wind potential by 56% and 89%, respectively. So for the rape straw generation, rape straw utilization for electricity generation, it could be used to reduce the global wind potential of large-scale and small-scale systems by 2.43% and 7.86% respectively. And for the glass straw disposal, if we incinerating glass straw instead of a recover it will increase global potential by 30.9% for large-scale development and 40.3% for small-scale development. The greater increase for small-scale development is because about 3.2 times of glass straw produced for small-scale development as compared to their large-scale development. So after the sensitivity analysis, we try to explore alternative configurations and see how it's gonna help us to deliver a better option for biodiesel production in the UK. So we consider a few different methods. The first one is to switch into low nitrogen nutrient methods for rapeseed cultivation. And the second one is to use B20 to displace the fuel in rapeseed farming and seed drying and cooling. The third one is to replacing the electric gas-based heating by utilizing rape straw. So this is for large-scale development. There changes we made to improve the global potential of the development. But small-scale development, we consider still this ABC3 changes plus a 66% additional oil extraction from the cold oil press. And this help us to, significantly improve the carbon footprint of the development. So it could help to reduce, for the large scale development, 40.1% of global warming potential. And for the small scale development, 33.6% of global warming potential. So for the other details, I will skip here for now because of time constraint. So that is the first part of the talk, which is about clarifying some kind of case study we carry out for understanding bioenergy waste management in Glasgow in the UK. The second bit is about application of machine learning based methods. So one very important reason why we carry out machine learning based methods that when we trying to do the life cycle assessment, we are facing the difficulties to get a quality input data, specifically, for example, for the processes we considered in this development. And also we find this limits our flexibility in design or optimizing this kind of development. Therefore, we're trying to say, okay, use this kind of machine learning based method to help us develop models that could be used to quantify the changes in the influences of their changes in the process conditions on the productivity of productions of this kind of waste management and bioenergy production technologies. And we can see in the literature the application of machine learning is increasing over the years, and it's air cold waste increasing accumulation of the quality data for the different technologies that could be considered for advanced waste management or bioenergy generation. The very first model we consider is for gasification, and we review the existing machine learning models. We find actually they're quite limited. They are limited to a specific type of feedstock, limited to specific type of configuration, or they are not considered many, for example, reactor types, or consider the types of the use of a catalyst. So we try to mitigate the weakness of those existing models. We try to develop a more comprehensive machine learning model for predicting the production of gasification technology. So to achieve so, we gathered a database which covers a wide range of feedstock types, different gasifying agents, different reactor outputs. We also considered categorical variables in the machine learning models, which has often been neglected. And we found this kind of variations in the model inputs and outputs will be helpful for us to carry out a more efficient life cycle assessment.
Hello, Simi. Can you hear me? Sorry to interrupt. It's already over time for more than 10 minutes. Maybe you can quickly flash your rest slides.
Sure. Yeah.
Thank you.
So, okay, no problem. So what we do is that we basically develop the machine learning based models, and for gasification, this is of higher generalizability. So it could be applied for different feedstock, different process conditions, reactor types, use of catalysts, and we consider about the influences of those categorical variables on the production of the gasification process. And in general, the models we developed could achieve a reasonably high accuracy in predicting gasification production, but there are two products that this kind of model perform particularly worse, which is about char yield and hydrocarbon generations. This is because for these two type of generations, the data the data that are available in the literature is relatively a few, so which limits their performance of their machine learning developed. And then we also developed models to interpret the models, machine learning models, and understand how those models actually make predictions for the gasification technology. Following that, we change the technology, we consider pyrolysis, and we consider, okay, the pyrolysis technology is a very important one that could be used to generate biochar for soil application. And we recognize the biochar yield and the compositions both are very important factors for us to estimate its impacts on soil and its impact on the global warming potential. So we developed two models, one based on their neural network, another based on the AMPHIS, to predict their biochar yield and compositions. And this model will be then combined with life cycle assessment to understand how a biochar application could be optimized or improved upon its soil application. The last bit is about integrating anaerobic digestion with heat pump. And we utilize machine learning based method to model the anaerobic digestion process. And then that help us define the optimum temperature required for the anaerobic digestion process. And the temperature help us to then define the capacity, define the process for the heat pump utilized in this integrated development. We then apply this integrated model in the life cycle assessment to compare the carbon saving potential, or to evaluate, quantify the carbon saving potential of this integrated system as compared to existing natural gas-based anaerobic digestion systems. And it shows that about up to 30% of the carbon dioxide could be saved upon this new configuration. So I think that's it for my talk today. I'm sorry that the time is not that managed well. And I hope you found this talk useful. And I wonder if there's any questions.
So thanks, Simi, for the nice sharing on the bioenergy and the waste management. So may I invite the audience to ask questions if you have. So Simi, just make sure you can hear me, right?
Yes, yes.
Okay. So yeah, so if you have any questions, just raise your hand.
Hi, Professor Yu. I have one question on. Thanks for that presentation. I just wonder if we what's your comment maybe how to accounting for the future improvement on the fossil fuel resources structure, like the compositions of the biofuels and the fossil fuels in the future scenarios within your study?
Thank you, Xian. I think it's a very good question. So I'm not so sure if that is related to about carrying out a consequential life cycle assessment, which taking the future changes in the whole, say, energy mix in the system. But for what we have carried out in the UK, for the studies about the UK, we try to use the existing data about the existing energy supply in the UK. So we haven't explored yet how that's going to affect the development, if this kind of energy supply in the UK or mix been changed in the future. But it will be worth exploring in the future, I think. I'm not so sure if that addressed your question.
Yeah, I think thanks for answers. That can answer my question. And the follow-up maybe comes with like, is there any feasibility to use the machine learning tools, like maybe like AI tools to simulate or to accounting for the like the future, not the future energy mix, but more like the future scenarios in the biofuel or the fossil fuel production? Because I think in some of your studies mainly more on the current scenarios, that is maybe like business of business as usual scenarios. But I think to meet the future energy needs, we also need to think about how the fossil fuel production or how the renewable fuel production can meet the future need.
Yeah, I think it's possible, but it depends on the data availability. If you have such temporal data or quality data that allows you to evaluate the variations of the needs of the fossil fuels along the time. If the data available, I think it's possible to develop a model. I think there are some other existing models that are available, not necessarily in machine learning model, that could be helped to predict the changes in this kind of economics related information or data. Yeah, so it's not necessarily in machine learning, and I think I believe that some other models methods available to do the same thing.
Okay, thanks for your answer, Professor.
Okay, do we have further questions for Dr. Yu? If no further questions, so thanks Dr. Yu again for the nice sharing, and thank you all for your joining.
Thank you.